right, so once again, now we're trying to formulate requirement number 4, so which says that either this constraint will be satisfied or this constraint will be satisfied. So basically, in between, we have this OR requirement. Okay, so once again, if I just sort of go ahead and add these constraints to my model, so if I go ahead and add this one and this one to my model, then I'm going to force both of them to be satisfied. Okay. However, what I want to do is I want to have some flexibility. So I want to make sure that I'm going to either satisfy this one or I'm going to satisfy this one. Okay. And there was a suggestion in which we basically add up these two constraints, and we also add up the right-hand sides. But I just mentioned that that doesn't work basically because, for example, some feasible solutions will not be satisfied by that constraint. Okay. So for example, I can pick this one and this one, in which case I'm going to satisfy the first constraints, and I can pick nothing from this one. But if I add them up, then the left-hand side will be 2, the right-hand side will be 4, so as a result, this will not be satisfied. Okay, so as a result, adding up the 2 does not work, so we have to do something else. So let me rewrite these constraints again. So the first one is x1 plus x2 plus x3 is greater than or equal to 2, or x4 plus x5 plus x6 plus x7 plus x8 is greater than or equal to 2. Now here comes a crucial observation. Okay, so essentially what I want to do is I want to satisfy either the first inequality or the second inequality. Okay. So if you think about this a little bit, I actually have a choice here. Okay, I can choose to satisfy either this one or this one. Okay. So I don't know in advance which one I'm going to pick to satisfy. So whichever actually works better for me, I'm going to pick that one. But I don't know in advance which one I'm going to pick. So as a result, one way to think about this is, so there's another yes/no type decision here, basically. Okay, so will I satisfy this constraint or not? And will I satisfy this constraint or not? Okay, so whenever we have a yes/no type decision, that actually calls for again a binary variable. Okay, so what I'm going to do is I'm going to define a new binary variable now. Okay, and I'm going to call it y, and I'm going to define it as follows. So let me call this 1. And let me call this 2. So I'm going to set y equal to 1 if 1 is 1 is definitely satisfied. And I'm going to set it equal to 0 if 2 is definitely satisfied. Now let me try to explain what this means. So in addition to my xj's, x1 through x10, I'm actually defining yet another binary variable, which I'm calling y. And I'm going to set it equal to 1 if 1 is definitely satisfied. So what does definitely satisfied mean? So my variables make sure that this constraint will be satisfied. So y will be equal to 0 if I make sure that the second constraint is satisfied. So by picking y equals 1 or 0, I make sure that either the first one or the second one will be satisfied. Okay? So one way to think about this y variable is that it sort of gives my preference. Okay? If y is equal to 1, I want to satisfy this. And if y is equal to 0, I want to satisfy this, basically. Okay? And since y can be only 1 or 0, then I make sure that either this one or this one will be satisfied. Okay? Now the question is the following, of course. So there's one thing you have to be careful about when you formulate a problem. So whenever you define your variable this way, okay, y is equal to 1 if something happens and y is equal to 0 if something else happens, your model has no idea what yj is, or what xj is and what y are, basically, okay? So you need to tell your model the relationship between xj's and y, okay? So in other words, what we want to do is we want to write constraints so that if y is equal to 1, then this will be satisfied, and if y is equal to 0, then this will be satisfied, okay? So as I said, I mean, despite the fact that you define your decision variables this way, your model has no idea about what y means. Okay? So, sorry? Say again?
Can we do y times y times 1 plus y times 2? Isn't it a constraint?
So you're saying that I'm going to multiply this by y. What's the problem with that? So once again, we're multiplying variables, right? So never ever multiply two variables. Okay? So then you're not going to have an LP problem. So as a result, this is not going to work. Okay? So once again, one thing that's important to realize is the following. So if I go back to this definition, so I'm defining xj to be 1 if project j is chosen and 0 otherwise. When I write down this model, my model has no idea what xj means. Okay? It's my duty to tell my model that xj means something. Okay? And the only language my model speaks is these constraints, basically. Okay? So the constraints are the only way I can sort of communicate my intentions to my model. So as a result, once again, I'm defining this variable for myself. Okay? But I need to tell my model that this variable does what it's supposed to do. Okay? So what does that mean? So basically, what I want to do is I want to write constraints. I want to add constraints to my problem in such a way that when y is equal to 1, I'm going to make sure that this constraint will be satisfied. And when y is equal to 0, I'm going to make sure that this constraint will be satisfied. Okay? So how do we do that? Well, let me start with the first requirements. So x1 plus x2 plus x3. So the right-hand side is 2. But I want the right-hand side to be 2 if y is equal to 1. Okay, so let's see if that works. So what if I actually have this constraint? So let's think about this a little bit. If y is equal to 1, then the right-hand side becomes 2. Okay? So which means that then I'm actually forcing the first constraint to be satisfied. Now what happens if y is equal to 0? Well, if y is equal to 0, then the right-hand side becomes 0, right? Well, if the right-hand side is 0, then this constraint does not mean anything at all, basically, right? Okay? So as a result, we say that this becomes a redundant constraint, an extra, an unnecessary constraint, so to speak. Okay? So which is good, because if y is equal to 0, I may or may not satisfy this one. Okay? I'm not forcing to satisfy this one. I only want to make sure that if y is equal to 1, I want to force this one to be satisfied. Okay? If y is equal to 0, then the right-hand side becomes 0. So this just becomes a redundant constraint, an unnecessary constraint. So as a result of which, this may or may not be satisfied. I don't care. Okay? All I do care is that if y is equal to 1, I want to make sure that this is satisfied. Okay? So how about the other one? So if y is equal to 0, I want to make sure that this one is satisfied. So let me start again with the left-hand side. x4 plus x5 plus x6 plus x7 plus x8 is going to be... So once again, for the right-hand side, I want to pick something. I want to write an expression that depends on y in such a way that when y is equal to 0, right-hand side becomes 2. Okay? So the question is, how can I write that? So what should I write on the right-hand side? Well, 2y doesn't work, right? Because if y is equal to 0, then the right-hand side becomes 0. So, sorry? 1 minus y doesn't work either, because if y is equal to 0, then right-hand side becomes 1. But I want right-hand side to be 2. 2 times 1 minus y will work. Okay. So, well, so once again, let's think about the different cases. If y is equal to 1, then the right-hand side of the first constraint becomes 2. In which case, this is always satisfied. Okay? And if y is equal to 1, then the right-hand side of the second constraint becomes 0. Okay? Which means that the second inequality may or may not be satisfied. Okay? So in other words, when y is equal to 1, this constraint becomes redundant. Okay? So this constraint does not impose any restrictions, basically. Okay, on my choices. On the other hand, if y is equal to 0, then the right-hand side of the second constraint becomes 2, in which case this is always satisfied. And the right-hand side of the first constraint becomes 0, in which case this constraint, the first constraint, does not impose anything at all. Okay? So as a result, by writing these constraints, by adding these constraints to my problem, I make sure that at least one of these two constraints will be satisfied. Okay? And which constraint will be satisfied will depend on the value of y. Okay? If y is equal to 1, then the first constraint will definitely be satisfied. Okay? And if y is equal to 2, y is equal to 0 rather, then the second constraint will always be satisfied. Okay? There's one thing that you should sort of well, so there's one point that might not be clear. So if y is equal to 1, I make sure that the first constraint is definitely satisfied. Okay? However, if y is equal to 1, I'm not saying anything about the second condition. Okay? That's important. Okay? Why is that? Because I may satisfy both of them at the same time. Okay? That's a possibility. So what I want to do is, if y is equal to 1, I want to make sure that at least this is satisfied. And if y is equal to 0, I want to make sure that at least this is satisfied. Okay? So by writing these constraints, I make sure that basically at least one of these two constraints will always be satisfied. Does everybody see that?
How can both be satisfied if y is 1?
If y is equal to 1, then this is satisfied. And the right-hand side of this one becomes 0. But all of them can still be equal to 1, basically, right? I can still pick two projects from here. The constraint will still be satisfied. So if y is equal to 1, I'm not saying that I cannot pick anything from here. If y is equal to 1, I'm just saying that from the second requirement, I don't have any restrictions. I may still satisfy the second restriction or not. I don't care. Okay? So here's what I'm saying. So I can pick, for example, 2 from here and 2 from here, basically, right? That's a possibility. If y is equal to 1, then this will be satisfied. And if y is equal to 1, this is 0, but the left-hand side is still 2, so I'm still picking 2 projects from here. So I'm not sort of preventing that from happening. That's what I'm saying. Okay? I'm just not forcing this one. Okay? I'm not forcing this one, but this may still be satisfied. That's what I'm trying to say. So once again, I mean, this is important, and I just want to make sure that everybody understands this. So the value of y actually tells you which requirement will definitely be satisfied. Okay? That's important. And the value of y, for example, if it's equal to 1, it tells you that 1 is definitely satisfied, but it doesn't tell you anything about 2, basically, okay? So it just doesn't force 2 to be satisfied. Okay? Similarly, if y is equal to 0, then it forces 2 to be satisfied, but it doesn't have any effect on 1. 1 may or may not be satisfied still. So by picking y either equal to 1 or 0, I make sure that at least one of them is satisfied, and that's what I want, basically. Okay? So how do we write these constraints? Well, we write them in the following way. So, for example, if y is equal to 1, 1 is definitely satisfied. So when y is equal to 1, I want to make sure that this constraint is the same as this one. Okay? And similarly, if y is equal to 1, I want to make sure that the other constraint becomes a redundant constraint. Okay? So the other constraint does not impose anything at all. Similarly, if y is equal to 0, I just want to make sure that the right-hand side of this constraint is the same as this one. Okay? And if y is equal to 0, then the first constraint now becomes a redundant constraint. So it does not impose any restrictions. Okay? So as a result, by adding these constraints to my problem, I make sure that at least one of these two constraints will be satisfied. Does everybody see that? Any questions? Yes?
Without doing all this, can we, like say, give numerical values to 1 and 2? Like if we say more than 1 and 1, or 1 and 2, and we sum 1 and 2, and we can say greater or equal to 1. Is it also okay?
Okay, I didn't quite understand that. So
without we forget y.
Okay.
And just say to 1 or 1 and 2, like we give birinci, ikinci yaptık ya, 1, 2 diye şey verdik, isim verdik.
Okay.
O sayı isimlere 1 diye değer versek ikisine de 1 olarak, yani 1 ve 1 eşit, 2 de 1 eşit. Toplasak 1 ve 2 ve 1'e büyük eşit desek, yani ikisinden biri elbet 1 olacak, diğeri ne olursa olsun gibi düşünüyorum. Birinci denklemle ikinci denklemin toplamının, ama yani sadece sayı olarak onlara sayı veriyoruz. 1 diye sayı verdik ikisine de. İkisinin de toplamı birden büyük olacak desek, büyük eşit olacak. O da yeterli olur mu?
Well, so first of all, this one is not a number, okay? So this one just represents the first constraint.
Yes, ben de anlıyorum. İşte o
Okay?
o birinci denkleme 1 diye bir isim versek, ikinciye de 1 diye bir isim versek, ikisinin de olması, hani toplamı birden büyük eşit olacaksa eğer, hani birinin sağlanması yetiyor anlamında.
Well,
İkisinin de doğru olup olmadığını denetleyen bir binary variable tanımlasak diyor. Sonra ikisini topluyor en az bir desek.
well,
Çarpman lazım.
well, we're actually doing that in some sense, right, aren't we? So what I'm doing is the following. So I'm defining y equals 1. I'm defining y equals 1 if 1 is always satisfied, and I'm defining y equals 0 if this is always satisfied, and y is either 1 or 0. So at least one of them will be satisfied, basically. Okay. Okay, so once again. Okay, so once again, I mean, so one thing you have to pay attention to is the following. Okay, so I want to make sure that either the first constraint is satisfied, which is this one, or the second constraint is satisfied. Okay, or both of them can be satisfied as well. Okay, so I'm also allowing the possibility of both of them to be satisfied. Okay, if you like, you can satisfy both of them. So as a result, I'm defining my new binary variable in such a way that, so if y is equal to 1, then I'm forcing this one to be satisfied, but it has no effect on this one. And if y is equal to 0, I'm forcing this one to be satisfied, but it has no effect on this one. Okay? So as a result, if you look at this sort of formulation, then it's not too hard to see that, for example, any possible choice will satisfy these constraints. Okay? So for example, I can just pick 1 and 2 from the first pool, and I can pick nothing else. Then I'm going to set this one to 1, this one to 1, this one will be 0, y will be equal to 1, and here it's going to be 0, the right-hand side is 0, so everything is satisfied. Okay? Or I can pick just 2 projects from here. Then, for example, maybe this one will be 1, in which case y will be 0, so I'm going to satisfy this. Then everything else is 0, 0 is greater than or equal to 0, so everything is still satisfied. Okay, so as a result, basically, I just want to make sure that at least one of them is satisfied. Yes? Question?
Hocam, ya bu çok mükemmel de ben daha basit bir şey yani ben bunu şunun aslında düşündüğüm şeyi söyleyebilir miyim? Hani, Y1, Y2'ye yazsaydık, Y1 birinci constraint için, Y2 ikinci constraint için, birinci sıfır olsaydı, öyle yazsaydık, Y1 artı Y2 işte büyük bir 1 olsaydı.
Ya anlatamıyorum.
Okay, so yes, okay. That's a good question. Okay, that will also work, but then you need to define 2 variables. I'm defining only 1 variable. Okay. Yes, provided that you write them correctly. Okay, so if you write them correctly, then of course. No, you can say y1 plus y2 is greater than or equal to 1. Okay, so we'll talk about later. Other questions? Yes.
Hocam, şimdi birinci denklem sağlanacağı zaman Y1 olacak ve ilk taraf o zaman ilk denkleme eşit olacak. İlk yazdığımız alttaki bir x1, 2, 3'ün toplamı işte 2'den büyük birinci denkleme eşit olacak. Aşağıdaki de o zaman sıfırdan büyük eşit olacak. O zaman ben sadece bir tanesini seçebilirim. Bu bizim sınırlarımızın dışında kalmaz mı?
Sorry, I didn't understand the question.
Birinci denklem sağlanıyor. Y eşit 1 oldu. O zaman x1, 2, 3'ün toplamı 2y'den büyük olduğumuz birinci denkleme eşit olacak. Ama aşağıdaki denklem sıfırdan büyük eşit oluyor ve o zaman sadece bir tanesini seçebiliriz. Ama sadece bir tanesini seçemiyor oluruz.
Why not?
At least two seçmeliyiz.
Well, I'm satisfying the first one already, right? I'm picking 2 from here already. So I'm already satisfying this. I may not satisfy the second one. Okay. So okay. Once again, I mean, let me just sort of repeat this once more. Okay.
Yani şöyle bir şey var. X1, 2, 3 eğer 2'den büyükse diğerleriyle ilgili herhangi bir constraint olmayabilir.
Exactly. Exactly. Yes. Yes. So basically, what this means is the following. Okay. From these 2 constraints that I call 1 and 2, okay, I want to make sure that at least one of them will be satisfied, and I claim that by doing this, I achieve that goal, basically, okay? So I make sure that at least one of them is satisfied, okay? And that's all I want, okay? So all I want is basically just make sure that from these 2 constraints, at least one of them is satisfied. And since by the help of my binary variable y, I make sure that this is satisfied, okay? So one thing you have to pay attention here is the following. So once again, once you define your binary variable this way, so you have to pay attention to these constraints, how you write these constraints. if y is equal to 1, I want to make sure that 1 is definitely satisfied, so which means that I want to make sure that the first constraint coincides with this one actually. Okay? And if y is equal to 1, then the other constraint should become a redundant constraint, which means that it will always be satisfied. Okay? Regardless of, in other words, this does not impose any restrictions on your variables. Okay? On the other hand, if y is equal to 0, then I want to make sure that the second constraint actually coincides with this one. Okay? And if y is equal to 0, now the first constraint imposes no restrictions. So that's the way you should set it up. Okay? And if you do it that way, then you make sure that at least one of them is satisfied. Both of them can still be satisfied. Okay? That's okay. My constraints still allow that. Okay? But what I'm interested in is I just want to make sure that at least one is satisfied, and these make sure that at least one will always be satisfied. Okay? Any other questions? All right, so now let's work on the last requirement. So basically what I'm going to do is that I'm going to add these two constraints to my model. Okay? So this one and this one will be added to my model. So this is requirement number 4. So now let's figure out the fifth one. If at least one of 1 and 2 is chosen, then at least one of 9 and 10 will be chosen as well. Okay? So what does this mean? Well, so if x1 plus x2 is greater than or equal to 1, so if this is satisfied, okay, this implies that x9 plus x10 should be at least 1 as well. Now, again, this is a sort of different sort of kind of constraint. So basically, you know, think of this as my condition. Okay? If I happen to satisfy this condition, then I should also satisfy this condition. Okay? So if I pick at least one project from this pair, then I should at least pick one project from this pair as well. Okay? So now the question is, how can I formulate this as a problem, as a constraint? Now, there's one thing you should pay attention to, which is I want to enforce this constraint only if this condition is satisfied. Okay? And if this condition is not satisfied, then I don't need to enforce this constraint, basically. Okay? So, how can I write this as a constraint? How can I model this? Does this work? This can be equal to 1. This can be equal to 0, basically, right? So I can still pick one project from here, and I can pick nothing from here. Now, there's one thing that I'd like to draw your attention to. So, in the previous requirement, we saw that if we have two constraints, okay, and if at least one of them is satisfied, then we can model it. Okay? So here we have like an if-then constraint. If something happens, then something else should happen. Okay?
We can say, instead of y, we can say that it's 1 if x1 plus x, at least one of them is chosen, and 0 otherwise. Then we can say x1 plus x2 greater than or equal to, or equal to x9 plus x10. Right?
Okay. That might work. That would be one way of doing it. So another way is the following. So this is the way I like more. So we have, you know, a proposition implies another proposition, right? Okay. And over here we have a proposition or another proposition. Okay. So the question is basically, can I take this and turn it into this form? Okay. So do you still remember high school math? So how can I model this constraint? P implies Q. Well, this is the same as not P or Q, right? Do you remember this? So this is basic logic. Basically, this proposition, okay, P implies Q is equivalent to not P or Q. Okay? So as a result, what I can do is I can take this constraint. So think of this as my P. And this is going to be my Q. And I can write it in the form of the previous requirement. Okay? So what am I going to do? I'm going to negate the first proposition. Okay? So what's the negation of the first proposition? x1 plus x2 is not greater than or equal to 1. Okay? So what does that mean? If it's not greater than or equal to 1, so x1 plus x2 will be strictly less than 1. Okay? Which I can write this as x1 plus x2 is less than or equal to 0. Okay? So you may wonder why not equal to 0? Well, because this is going to help us basically. Okay? So, or x9 plus x10 is greater than or equal to 1. So now I'm in exactly the same sort of framework as I was in requirement 4. So now I have two constraints. I will either satisfy this one or this one. Okay, at least one of them should be satisfied. Okay? And I'll just play exactly the same game. Okay, so I'm going to define a new variable. So I'm going to call this number 3, and this one is number 4. So I'm going to define a variable z, a binary variable z. It's going to be equal to 1 if 3 is definitely satisfied. And it's going to be equal to 0 if 4 is definitely satisfied. Now I need to write down the constraints. I need to relate 3 and 4 to my new variable z. Okay. So let's just do it as a sort of new exercise. So x1 plus x2. On the right-hand side, I want to write an expression so that if z is equal to 1, then the right-hand side will be 0. And if z is equal to 0, then this does not impose any restrictions. Okay? Now, the question basically is the following. So, when can such a constraint impose no restrictions at all? Well, if I make the right-hand side 2, for instance, okay, then this will always be satisfied, right? Why? Because both x1 and x2 can only be 0 or 1. Okay? So as a result, in the previous case, we were trying to make the right-hand side 0 because we had greater than or equal to constraints. Now we have a less than or equal to constraint. So we need to make the sort of right-hand side large enough if z is equal to 0, basically. Okay? So what's the right expression that I need to add here? So once again, what I want to do is I want to make sure that the right-hand side becomes 0 if z is equal to 1. And the right-hand side becomes 2 if z is equal to 0. Where does 2 come from? Because if the right-hand side is 2, then basically this constraint is always satisfied. Okay? This becomes a redundant constraint. Does everybody see that? Okay. So the question is basically what should I write on the right-hand side? So let me start with 2. And I'm going to multiply 1 minus c exactly. Okay? So let's see if this works. If c is equal to 1, then this becomes 0. The right-hand side becomes 0, in which case I have exactly this formulation. If z is equal to 0, then this one becomes 1. 2 times 1 becomes 2. So this is always satisfied. This becomes a redundant constraint. Does everybody see that? So let me work on the other one. x9 plus x10. So now I want to pick an expression for right-hand side such that when z is equal to 0, the right-hand side becomes 1. And when z is equal to 1, the right-hand side now becomes 0, right? So now becomes a redundant constraint. Okay? So what should I write on the right-hand side? So let's see if this works. If z is equal to 0, then 1 minus c becomes 1, and I just achieve this constraint basically, right? And if c is equal to 1, then the right-hand side becomes 0, so this becomes a redundant constraint now. Okay? So as a result, by adding these two constraints, I make sure that at least one of the two will be satisfied. Okay? So once again, I mean, it seems complicated, but it's actually pretty straightforward. The only thing you need to pay attention to is the following. So whenever you have a constraint with less than or equal to or greater than equal to relationship, if z takes the value of what you want it to take, for example, in number 3, then you want to make sure that the right-hand side of this, the first constraint, becomes the same as the right-hand side of this constraint. Okay? So in other words, if z is equal to 1, then the right-hand side becomes 0, so you just recover this constraint. If z is equal to 0, then you want to pick a value for the right-hand side so that this constraint does not have any restrictions on you. Okay? And indeed, if z is equal to 0, then the right-hand side becomes 2. So as a result, x1 plus x2 is always less than or equal to 2, so this becomes an unnecessary constraint, so to speak. Okay? Similarly, if I look at the second one, so if z is equal to 0, then I want to make sure that this constraint is the same as this one. Okay? And indeed, if z is equal to 0, then I just recover this constraint. And if z is equal to 1, then the right-hand side becomes 0, in which case this one becomes a redundant constraint. Okay? An unnecessary constraint. Okay? So as a result, basically, by adding these constraints to my model as well, I just make sure that at least one of them will be satisfied. Okay? One question. So for example, instead of having x1 plus x2, if we had x1 plus x2 plus x3, how would the right-hand side change in that case? So instead of 2, we would have 3 times 1 minus c. Okay? So then 3 makes this constraint redundant. Okay? If I have, let's say, 10 variables, then this would be 10 instead of 2. Okay? That would be the only change. But the basic logic is the same. So you just want to make sure that if the variable takes the value corresponding to that constraint, you want to make sure that that constraint is the same as constraint number 3. And if it takes the other value, then you just make sure that that constraint becomes a redundant or unnecessary constraint. Okay? So it doesn't impose any restrictions on you. Is that clear? All right. Any questions? Yes.
I was thinking about another solution.
Okay.
Say x1 plus x2 equals x9 plus x10. And this will only miss one part is 1 and the other part is 2. Otherwise, it will satisfy all dimensions of the solution. And in order to fix the missing part, maybe we can say x1 plus x2 minus x9 equals to 0, and x1 plus x2 minus x10 equals to 0 again.
Well, okay. So as soon as you add this constraint, you're already in trouble, basically. Okay. So you already you already make sure that x1 plus x2 should be the same as x9 plus x10, and this doesn't work for a lot of reasons. The first one is that, for example, this can be 2 and this can be 1, so that's not going to work. Also, if this is not satisfied, so this can be 0, but you can still satisfy this. That's still okay. Okay? So basically, you just want to make sure that if this is true, then this has to be true as well. But this may not be true, but this can still be true, basically. Okay? So in order to satisfy this, you don't need to satisfy. It's not necessary that you satisfy this one. Okay? So basically, this constraint is independent in some sense. Okay? You may still satisfy this constraint without satisfying this one. This only says that, if this happens, then this has to happen. But in order for this to happen, this may or may not happen, basically, okay? So think of this as, for example, if it rains, then you get wet.
I was thinking the only problem is just 1 is 2 and the other one is 1 or 1 or 2. Then we can fix this, but I couldn't see this.
No, so once again, I mean, this is important. So think of this in the following way. So, for example, if you work hard, then you get a good grade, basically, right? So this would be an example of proposition. But just because you get a good grade does not mean that you worked hard, basically, right? So you can cheat and you can still get a good grade, okay? So as a result, basically, this only says that, I mean, if you work hard, then you know that you're going to get a good grade. But there might be other ways of getting a good grade as well, right? So, get along with the professor and so on and so forth. So basically, there are other ways of doing that. Yes? Which solution?
Z is equal to 1 if x1 plus x2 is bigger than or equal to 1, 0 otherwise, and x9 plus x10 is bigger than or equal to 1, bigger than or equal to z.
I think so, but what I want you to do is I want you to actually learn it this way, because I think this is a lot easier. Okay? So, first of all, always take any requirement and turn it into, something or something else. And after that, I think it's pretty easy, actually. Okay? So, if you do it the other way around, then it's more like that you make a mistake. So, this one is definitely easier to understand and do. Yes? That's a good question, because essentially, if I use the same variable y here, that's your suggestion, I guess, right? Then what I'm doing is I'm relating this requirement to this requirement at the same time. So I'm saying that, for example, if 1 is satisfied, then 3 is also satisfied, or something like that. Okay? So if I use the same variable y here, then, if y is equal to 1, then 1 is satisfied. If y is equal to 1, then 3 is satisfied. So basically, every time I satisfy 1, I also satisfy 3. But this may not be the case. So essentially what I'm saying is that, which of these two requirements I'm going to satisfy, I don't know in advance. Okay? And which of these two I'm going to satisfy, I don't know in advance either. And these two are completely different from these two. Okay? So as a result of which, I cannot use the same variable y here. Because if I use the same variable y, then if y is equal to 1, I'm forcing this one to be true. If y is equal to 1, I'm forcing this one to be true at the same time. So which means that then I'm actually relating that if this is true, this has to be true as well. Okay? Do you see that? Okay? But they're completely independent from one another. So that's why I need a new variable. Okay? Other questions? All right, so now I'm going to give you a few more examples. So this is a sort of, one of the most complicated examples that we have seen so far, but it tells you that you can use binary variables in a lot of different settings as well, and logical constraints is one of them. Okay, so you cannot formulate such constraints without using binary variables. Okay, so which means that binary variables are quite helpful in terms of extending the kind of formulations or problems you can formulate. Okay, and as I mentioned, this type of constraints arises in a lot of different settings. So, for example, when you sort of, do your registration for your courses, the program actually uses a similar similar logical constraints. Okay, so if you don't take Math 225, you cannot take IE-202. If you didn't take IE-202, you cannot take IE-303, and so on and so forth. So there's a lot of similar logical constraints. Or you can take at most, for example, 2 or 3 math courses in a semester, or something like that. Okay, so as a result, this type of constraints arises in a lot of different settings, and we can formulate them using binary variables. So now I'm going to tell you a few other uses of binary variables as well. Example 19. So this is the first part. So suppose that the production capacity of product J is AJ, where J goes from 1 to n. So suppose that if the company chooses to produce product J, then at least LJ units should be produced. So here J goes from 1 to n. Now I'm not going to give you the whole formulation, but suppose that this is part of a problem. Okay, so suppose that you're solving a production planning problem, and you have n different products. Okay, so for each product you have a certain production capacity that we denote by A1, A2, all the way up to AN. However, there is additional requirement that if the company chooses to produce a certain product, for example, let's say the first product, then it should produce at least L1 units. Okay, so think of this as, there's a certain setup that you have to perform. So as a result of that, to justify that setup, you have to produce at least a certain amount. Okay, which is quite common in manufacturing, basically. So the question is, how can we formulate this as constraints? How can we formulate this requirement as as LP or IP constraints. Now this is kind of different because basically if you produce, then you have to produce at least LJ. Okay? So you're going to produce at least LJ or you're going to produce nothing. Okay? So the question is basically how can you write this as a constraint? So once again, I mean, we're facing the following decision, just like in the warehouse problem. So for each product, we're going to decide whether we're going to produce it or not. Okay, so that's a yes/no decision. Okay, so what I'm going to do is I'm going to define a binary variable, which I'm going to call yj. It's going to be equal to 1 if product j is produced, and it's going to be 0 otherwise. So from now on, I just use o.w dot. This just means otherwise for short. So similarly, I need another variable xj. So this is the number of units of product j produced. So j goes from 1 to n. Here again, j goes from 1 to n. So just like in the warehouse problem, there's a certain relationship between xj and yj, right? So what's that relationship? If yj is 0, then xj should be 0, okay? And if yj is 1, then xj should be at least lj, but xj cannot be more than aj. Okay? So in other words, here's a relationship. If yj is equal to 0, implies xj equals 0. And if yj is equal to 1, then xj should be between aj and lj. So these are kind of like logical constraints again. Okay? So my question is, how can we formulate these constraints? And actually, if you think about this a little bit, we have two-sided relations basically here. So if xj is 0, then yj should also be 0. And over here as well. So if xj is between lj and aj, then yj should also be 1. So there are two-sided sort of implications. Okay? Okay, so that sounds like a good suggestion. So let's try to do that. So xj, I'm going to write this less than or equal to aj times yj. Okay? And xj, I'm going to write this is greater than or equal to lj times yj. So first of all, are they valid LP constraints? Yes, because if I put everything on the left-hand side, remember aj is a parameter. It's not a variable. Okay? A constant times a variable plus a constant times a variable is less than or equal to 0. Same here. So does this actually work? Well, let's try to think of it in the following way. If yj is equal to 0, so this tells you that xj should be less than or equal to 0, right? This tells you that xj should be greater than or equal to 0. By combining the two, you get xj exactly equal to 0. Okay? If yj is equal to 1, this says that xj cannot be more than aj. This says that xj should be at least lj. You have exactly this requirement. Okay? Conversely, if xj is positive, okay, then in order to satisfy the first constraint, yj should be 1. Okay? Because if yj is 0, then you cannot satisfy this constraint. Okay? And similarly, if xj is 0, then that means that yj cannot be equal to 1 because then you will never satisfy this constraint. Okay? So as a result, by writing these constraints, you make sure that if you produce at least lj, but you cannot produce more than aj. So by simply adding these constraints, you make sure that you have your upper bounds and lower bounds on your production capacity. Any questions about that? So this is another nice use of binary variables. So by using binary variables, you can say that either produce nothing, or if you produce, then you produce at least 30, for example, or something like that. Okay? So you can actually formulate such type of decisions using binary variables. So once again, I mean, the key observation here is the following. So whenever you have a choice, okay, in terms of whether you want to do it or not, binary variables are always helpful, basically, okay? So, for example, here as well, the reason why we use binary variables is that because we can choose to satisfy which constraint we want, okay? Similarly here, we choose to decide whether we're going to produce product J or not, okay? So depending on that, we either make, we either produce nothing or we produce at least AJ. Yes?
We said that we cannot multiply variables, but aren't we in fact multiplying xj by 1 over yj? No, 1 over yj.
No, we're not. So, I mean, I can write this as xj minus aj times yj is less than or equal to 0. And I can write this as xj minus lj times yj is greater than or equal to 0, right? So as a result, I have a constant times a variable plus a constant times a variable is less than or equal to a constant. A constant times a variable minus a constant times a variable is greater than or equal to a constant. So as a result, everything fits into the format of an LP constraint. Okay?
No, what I was saying, can't we divide both sides by yj?
Of course you can, but why would you? I mean, if I can write this as this is what I want, basically, right?
Okay. It doesn't deny that we have it in an LP problem. That's an LP problem. That's
It can be written as an LP constraint. That's what I'm interested in. Okay? So whether I can write this as an LP constraint or not, and these are LP constraints. Other questions? Okay, I'll see you on Thursday.